Hello, welcome to the second video for advanced chemistry this semester. Last time we talked about what chemistry is, a little bit of introductory material there, and then we also spent quite a bit of time talking about how to classify matter into one of those four big categories, right? Actually, there were two big categories, and then each of those two categories had two categories within them. So the two big categories were pure substances and then mixtures. Pure substances could either be elements, like show up on the periodic table, or compounds, which are made of elements. And then the mixtures could either be homogeneous in nature or heterogeneous in nature. And as we discovered in reality, mixtures can kind of be in between homogeneous and heterogeneous. It doesn't necessarily have to be one or the other. It's a bit of a spectrum, and through our analysis and inspection of those mixtures, we can come to a conclusion of which side they lean towards, but it doesn't necessarily have to be one or the other. So, today we are going to talk about states of matter. So last time we talked about one aspect of a substance, right? Its classification, right? It's either a pure substance or a mixture. It's either an element, compound, homogeneous or heterogeneous. Today we're going to talk about another aspect that a substance might have or does have, and that is its state. Okay, so if one aspect is its classification, right, based on its composition, it's like what it's made of. Another aspect is its state. Sometimes these are referred to as phases of matter as well, okay? And you're going to be very familiar with this. This is not going to take very long for me to explain. I'm sure everybody watching this video is somewhat familiar with this topic. We're just going to cover it from a chemistry point of view, and then we'll be able to move on, okay? So, these are the three states of matter. Solid, liquid, and gas. Now, in reality, there are some other more complicated states or phases of matter. For example, a plasma. We're not going to be really getting into that level of detail in this course, at least not right now. So for now, we're going to be sticking with the three more basic and more common states of matter, which are solid, liquid, and gas. Okay? And this one slide here, this one diagram, really kind of says it all, or shows it all. If you were taking notes along at home, I would write down everything on this slide, including all of the arrows and all of the little details of each of these diagrams, which I'm going to go through right now. So, we're pretty familiar with these particle diagrams at this point. We've seen some particle diagrams in the last video and in the last assignment. Each of these little circles represents a particle. Okay, that could be an atom, that could be a molecule, but these are very, very small particles. Okay, in a solid, the particles of a substance, if that substance is a solid, those particles are nice and tightly packed together. Some people might think that they don't move, and while that is partially true, you can see that there are some little lines here which seem to be, based on the other pictures, indicating some sort of movement. The key thing here is that in a solid, the particles don't move past one another. They can move, really the better term would be like they can vibrate, kind of like a buzzing or a humming, and that does really happen. Okay, so particles in our universe are always moving to a certain extent. The key thing here when we're talking about solids, liquids, and gases is whether or not those particles are actually able to move past one another or to like change their orientation in relation to one another. In a liquid and a gas, they most certainly are. In a solid, they are not. And it is that property of the particles that gives solids their definite shape. Okay? So for example, my phone is a solid. If I were to drop my phone, which I'm not going to do, it's not going to change its shape, right? The impact on the ground is not going to cause the particles to, well, I guess if I dropped it from a really tall height, it might, but generally speaking, with solid shapes, solid substances, I mean, the particles are sort of locked into place, and so hitting something or something hitting them is not going to cause them to move past one another. That is different than a liquid. Okay, let me make my camera big here again real quick. So inside of my water bottle here, you can see that I have some water. Liquids do not have definite shapes, okay, and that is because the particles are able to move past one another. I can flip my water bottle upside down, and you can see that the liquid water that is inside of my water bottle will adapt to the shape of the container, and that is because liquid particles can move past one another. Okay, and then gases can do the same thing. All right, you are an object that is currently changing the shape of the gas, the air that's in the room. Right? Think of the air that is in whichever room you're sitting in or standing in right now. That air has a current shape. If you move your arm, or move both of your arms, or move your whole body, you are changing the shape of the gas, and that is because the gas particles are able to move around, move past one another, and so they have no problem adapting to the new shape that they need to adapt to. Okay, so just to review what we discussed right there. Solids have a definite shape due to the locked-in nature of their particles. Liquids have an indefinite shape, as do gases. Okay? And once again, just to mention this one more time, solid particles can move. Think of it more of as like a vibration, almost like a humming. All particles in our universe do move to a certain extent, even if they're in solid form. The only exception to that is if something is at the temperature of absolute zero, meaning the coldest anything can ever get. And that's actually what absolute zero is. Absolute zero is the temperature at which particles completely stop moving. It's not actually possible to get to absolute zero. It's more of a theoretical or hypothetical temperature, but there you go. Okay, so the next thing I'd like to talk about is the volumes of these different states. Okay, solid objects have a definite volume. Okay, so once again, I'm going to use like my phone as an example. When you observe like your phone or my phone, it's not changing its size or its volume. It's staying, the same size. And that is because, once again, if we think about how these particles are behaving, the particles are all nice and locked in to one another, right? They're not moving past one another. They're not expanding or expanding or like condensing. And so the overall shape of that substance, or the overall volume of that substance, I should say, remains constant or definite, okay? And liquids also act that way. Even though the particles can move past one another, right? They're not locked into position like solid particles are. There isn't very much distance in between the liquid particles, so you can't really squeeze them together to cause them to reduce their volume. And liquids do not, of their own accord, expand to take up more volume than they otherwise would. The amount of water that I have in this water bottle, the volume is not going to change. If you took a super powerful machine and tried to squeeze my water into a smaller volume, you're going to have a really, really difficult time. Once again, that is because of the way that the particles in the water are behaving. They are close to each other. They can slide past one another, but they are so close to each other that there's not really any room to condense into, right? There's just not a whole lot of room to work with. That is how gases differ from these other two. Gas particles, by their nature, are separated from each other. They do not often come into contact with one another. So it is actually pretty easy to condense or expand a gas because there is a lot of space and a lot of room to work with in terms of, how much space is in between the particles. If you've ever been to a fast food restaurant, which I believe most of you probably have, if you sit in the drive-thru, a lot of times you'll see a big shiny metal canister on the outside of the building. That canister usually contains the carbon dioxide that is used to carbonate soda or pop. The amount of carbon dioxide gas that is inside of that canister, if you opened up the nozzle and let it spread out to its natural volume, it would take up an immense amount of space. But because gases by their nature have space in between these particles, you can actually condense gases quite a bit. Okay, so you can scrunch these particles down. It requires energy to do, but you can scrunch these particles together and force them into a smaller volume than they would naturally adopt. So that is why liquids have a definite, solids have a definite volume, liquids have a definite volume, but gases do not. They can change their volume. Okay. And the last thing I want to talk about with this diagram here is these energy arrows. Okay. As you add energy to a system or provide energy to a system, the way that the particles will behave will change. Okay, so if you take a solid and you add energy to it, think of it as heating it up. Okay, so heating something up, or putting it on top of a stove burner or on top of a fire, providing it with energy. What you're doing is you're transferring some of that energy, whether it be thermal or otherwise, into the particles, right? So the particles are able to absorb that energy, and in this case right here, this red arrow would represent melting, right? That is what solids do when they absorb too much heat. They melt. And then one step further, if you continue to heat up the particles in a liquid, you can cause the liquid particles to separate from one another. They contain so much energy, they no longer care about staying close to each other. They'll just float off by themselves. And this red arrow here would represent boiling. Okay, so once again, if you are writing this down at home, this arrow here, this first red arrow, actually represents the process of melting, whereas this one right here represents the process of boiling. Okay, and so as you add energy to a system or to a substance, things travel in a left to right direction here. Okay, and in contrast to that, as you remove energy from a system or remove energy from a substance, things go in the opposite direction. Not many people know or can think of the name of what this arrow represents, things going from a gas to a liquid. A lot of people know what this is, liquid to a solid. Think about it for just a second. What is it called when something goes from a liquid to a solid? Think about water, right? Liquid water turns into ice. What is that called? It's called freezing, right? So that's what this arrow represents. Not too many people can think of this, or it at least takes them a little while to think of this. There's actually a few different terms for this. This is called condensation or condensating, okay? And there's another term for this that I am struggling to recall at this exact moment. I'm sure I'll think of it before the video is over, and I'll let you know, okay? But a good term for this is condensating, okay? All right. So I just mentioned those 4 changes in state, also known as phase changes. Okay, this is just a summary of what I was talking about before, in case you did want to have, in case you do want to have some bullet point written notes. One other thing that I would like you to know about are these 2 terms here that are underlined. So when you melt or boil something, so for example, going in this direction, right, left to right, when you add energy to a system, that is referred to as an endothermic process, okay? And then on the flip side, as you remove energy from a system or remove energy from a substance, that is called an exothermic process, okay? The way that I remember these terms, endo kind of sounds like into, right? The substance is gaining energy, energy is going into it. Endothermic, into, endo, kind of sound the same. And then for exothermic, the substance is losing energy or energy is exiting, right? Exit kind of sounds the same. That's how I remember the difference between these. Therm just means heat, okay? So that is sort of the last thing I need you guys to know about this particular topic. Your assignment is going to involve you thinking about these changes of state and then also creating some particle diagrams of phases or changes of state, phase changes, which I will talk about during our Zoom meeting. Okay? All right, well, this video is quite a bit shorter than the last one. Appreciate you guys watching, and I will see you in class next week.